All right, in this video, we are going to be doing more practice on justification. So let's say that we are given f of x, and for number one, we want to see at which x values as f of x is equal to 0, and we want to explain our reasoning. Well, this is simple. We are given f of x, so our zeros are just going to be -6, -1, and 6. And our justification, well, they're literally just our zeros, so you could just say that it crosses the x-axis, it touches the x-axis, and so forth. Now, number two says at what x value is f prime of x is equal to 0, and we want to explain our reasoning. So in this case, this is whenever we have a horizontal tangent line because we're given f of x. So here, this is going to be at -4, 2, and 6. Horizontal tangent line. Number 3 says on what intervals is f of x increasing? So here, remember, since we're given f of x already, just see where it increases. So from 4 to 2, and then from 6 to 10. So -4 to -2, 6 to 10. And then to explain your reasoning, well, of course, as your x value increases, so does the y values. At which x value does f of x contain a relative minimum? So in this case, we know that's going to happen at -4 and at 6. To justify, you could say that f of x stops decreasing and begins to increase. At which x value does f double prime of x is equal to 0? So this is whenever we are changing concavity. It might be a little bit hard to see, but notice how here we're changing concavity. Well, this one goes concave up. Then we're going to concave down here. So we're changing concavity at, let's say, -1. And then here we're concaving down. And then we're concaving up. So we could say at -1 and +4. So x is equal to -1 and x is equal to 4 because f of x changes concavity. Now, on what intervals is f of x concave down? Once again, how are we changing concavity? So here we are going from -1 to 4. We're concaving down. Now, in AP Pre-Calc, you guys talked about concavity. So thinking about our justification here and why it concaves down, we could say that the rate of change of f of x is going to decrease. So the rate of change of f of x is decreasing. And then for number 7, at which x value does f of x have a point of inflection? Once again, that's going to be -1, +4. Since f of x changes concavity. So that was simple. And that was f of x. Well, this time, what if I give you the same graph, except we have g prime of x? So for number one, we want to see which x value is g of x is equal to 0. Unfortunately, we don't really have information on when g of x is equal to 0. We're only given the derivative, so here, can't be determined. Two says, which x value is g prime of x is equal to 0? Well, since we're already given g prime of x, you're just going to look at your zeros. So once again, this is going to be x is equal to -6, x is equal to -1, and x is equal to 6. When is g of x increasing? Well, remember that g of x is increasing whenever g prime of x is greater than 0. So when is g prime of x greater than 0? We could say -7 to -6, -1 to 6, and then 6 to 10. Honestly, you can put endpoints, closed intervals at -7 and 10 because technically they are, increasing. Four says, at which x value does g of x attain a relative minimum? So remember, this is whenever we are having a sign change given my derivative here. So g of x has a relative minimum when g prime of x changes signs from negative to positive. This occurs at the point x is equal to -1. 5 says, at which values does g double prime of x equal to 0? So once again, we're going to be looking at our horizontal tangent lines. That is going to be -4, 2, and 6. Number 6 says, when is g of x concave down? Well, g of x concaves down whenever g prime of x decreases. So this occurs whenever we are from -7 to -4, and then from 2 to 6. Seven says, at which x value does g of x have a point of inflection? So remember, a point of inflection means that our derivative changes from decreasing to increasing and vice versa. So that happens at -4, 2, and 6. All right, and that was based off of g prime of x. Well, guess what? Plot twist. Let's say that I have h double prime of x, aka the second derivative of the same graph. Well, unfortunately, I can't do anything with h of x is equal to 0, so that can't be determined. Also, I can't find whenever the derivative is equal to 0 since this is h double prime of x, so that also can't be determined. Oh, guess what? We don't know when h of x is increasing also, so guess what? That can't be determined. Oh, guess what? This is the second derivative. I don't know where h of x has a relative minimum because we're not given h prime of x. We're given the second derivative. So again, number 4 can't be determined. But number 5, guess what? At which x value does h double prime of x equal to 0? That's my zeros at -6, -1, and 6. Oh. Yeah. Okay. Number 6 says, on what intervals is h of x concave down? Well, guess what? This is whenever my second derivative is less than 0, which we definitely have. So it is less than 0 between -6 and -1, and that's it. And then at which x value does h of x have a point of inflection? So where are we changing signs? We're only changing signs at -6 and at -1 here. 6 isn't really a point of inflection here. So we are changing signs. We have a point of inflection at -6 and -1. Because h double prime of x changes signs. All right, that's all on justification. In the next video, we will be talking about optimization, which is going to be a lot of fun.